Good evening. I'm Shafali Agarwal. I'm a research scholar at IIT Madras, and today we will have our 68th session on the topic of design of steel structure. So, in the sixth week, you might have studied about the design of gusset plate. So, in the previous week, we have seen what is gusset plate. So, here we will see how to design gusset plate, and then we might have studied about what are the lug angles, splices, and a definition of compression members. So we were studying about tension member till previous week. So this week we will start about the compression member. So if we go from the start, so what are the gusset plates? We already read about it that these plates are provided to make connection at the places where more than one member is to be joined. So if we have to join more than if you see in this figure, we are joining almost three members are being joined. So to join a three members, we need a gusset plate. Like this is our gusset plate, which will pull here. It will be our gusset plate. We will be joining one member, two member, three member. If we see in this picture form, see in our this figure. So sorry. So this plate is a gusset plate, and it will be joining more than one member. So normally, for example, will be when we are providing joints of in the truss members or truss girders, then we will join them using gusset plate. Second thing is the line of action of members meeting at the joint should coincide. So if you see in this figure, all the three plates which are joined by gusset member are meeting at the line of action or force line is joining at a one point. So that all the line of action should coincide at one point. Okay. So this is what a gusset plate is. So how to design a gusset plate? First thing is the shape and size of the gusset plate is decided on the basis of direction of members meeting at a joint. So if we see in the previous figure, uh, in what direction the gusset plate is provided and what is the shape of in what direction our members are being provided based on our members' direction and their line of action, our gusset plate size and shape will be designed. So in this case, all three are like in triangular direction. That's why our gusset plate uh, shape was in this pentagonal shape, right? Second thing is the plate size is decided to meet the specification of pitch and edge distance for the bolts to connect the members meeting at the joint. Okay, so firstly we have seen the shape and size. It depend on the direction of members meeting at the joint. Second thing is the size is decided to meet the specification of pitch. In the example we have seen, we are providing bolts, the bolt pitch and the edge distance of the bolts to connect the members meeting at the joint. Third thing is gusset plates are designed to resist shear, direct and flexure stresses acting at the critical sections. And last thing is it is usual practice to provide thickness of gusset plates equal to the or higher than the members that are to be connected to the gusset plate. So its thickness is almost equal to the member plate we are joining it. So that was what are the design specification of our gusset plates. Next thing is the lug angles. So see what are the lug angles. So these are the short length of the angle section used at the joint to connect the outstanding length of the member to reduce the length of the joint. So normally when we are if you see here, this is one member or gusset plate, and this is our angle section which is being joined to the gusset plate. So to reduce the length of this joint, we are adding one more extra angle that is called as lug angle. So what it is doing, it is reducing the length of the our joint of our angle section and gusset plate. So it will take stresses which it will take the extra stresses and will reduce the amount of angle section which is to be connected to our gusset plate. So for a tension member subjected to very large loading, the number of bolts or length of weld required to make its connection with other member may often become large. Therefore, the size of gusset plate become very large, which can be uneconomical. Second reason is for effective sharing of load, the leg angle is provided at the beginning of the joint. Okay, we already discussed. So to decrease this connection joint, so that we don't have to provide a very long gusset plate. First reason is that. Second reason is to distribute the loads in our angle section and gusset plate. So the lug angle is connecting to the outstanding leg of the main angle. Okay. Next thing is these are not very efficient in transmitting the load. Moreover, an eccentricity develops between the load and the CG of the bolt group. Thereby, the use of lug angles is generally avoided. Okay. And next thing is lug angles may be avoided by the use of unequal angle section with the larger leg as the connected leg and using two rows of staggered bolts. So, what are the disadvantages of our lug angle is, firstly, they are not very efficient in transmitting the load. And second thing is, when we are providing a lug angles, if you see the we are providing angle section will be very long and there is a small lug angle provided here. So there are chances that centricity is developed between the bolt line or between the CG or load and CG. And this centricity will cause the failure of our section. So therefore, we are avoiding lug angles. So what can be the solution for this thing? It can be we can use two unequal channel section, two unequal section and the section with larger leg as the connected leg and using two row of staggered bolts. So what we are doing, instead of using, we are using angle section. So we will use a longer length of angle section as a connecting leg and we are using two row of staggered bolts. Staggered will be like this. So we are using two lines of staggered bolts. So next thing is how we are designing our lug angles. So according to clause 10.12 of IS 800, there is a general procedure how you can design your lug angles. So if in case of main member is being an angle section, so lug angle is connecting to the outstanding leg of the main angle that we have already studied. When an unequal angle is used, so the load get distributed in the ratio of gross area of the connected leg and the outstanding leg. So lug angle and their connection to gusset or other supporting members shall be capable of developing strength not less than 20% in excess of force in the outstanding leg of the main member. And next thing is the attachment of lug angle to the main angle shall be capable of developing strength of not less than 40% in excess of the force in the outstanding leg of the angle. Okay. Next thing is if our main member is channel leg section. The first case is if we are using angle section, then first we are connecting it to the outstanding leg. And in case of unequal angle, our load is distributed in the ratio of gross area to the outstanding leg. And third is that load, how much strength should be there, and strength should not be less than 20% in excess of force in outstanding leg and not less than 40% in case of force of outstanding leg of angle section. This is the outstanding leg of main member. So next thing is, if we are using channel leg section, then what should be the conditions? The leg angle, as far as possible, should be disposed symmetrically with respect to the section of the member. Lug angle and their connection to gusset and other supporting members shall be capable of developing strength of not less than 10% of the force in the flange of the channel section. And third is attachment of a lug angle to the members shall be capable of developing strength of not less than 20% in excess of the force. Okay. So next step of our design in lug angle is, in no case we should provide minimum of 2 bolts or rivets or equivalent weld length for attaching our lug angle to gusset plate or any supporting members. And the effective connection of the lug angle shall be as far as possible terminated at the end of member connected. And next thing is the fastening of lug angle to the member shall preferably start in advance of direct connection of the member to gazette or other supporting members. So leg angle should be connected along with the main members or gazette plate. It should not be done at the last or later on. So this is what we are using as lug angle now. So next topic is splices and tension member. So we read about the gusset plates, then lug angles. Third thing is splices. So sorry, these are the type of members we are using when the length is less than the required length of our tension member. So in case of uh, in case of our tension member, if our total length of our tension member is smaller than the required length of the tension member, we are providing an extra plate called as splices. So if a single piece of equivalent length is not available, tension member are spliced to transmit the necessary tension from one member to another. So what we are doing, we are connecting two tension members using an extra plates, which is called as splices. Here you can clearly see the two members are connected using splices. Okay. So how these splices can be designed? First thing is the strength of splice plate and the bolts which are joining them should be able to develop strength equal to the design load. Second thing is when tension members of dissimilar thicknesses are to be connecting, packing filler plates are introduced. And the third thing is the design shear capacity of bolt carrying shear through a packing of filler plate in excess of 6 mm shall be decreased by a factor as given below. So in case we are designing shear capacity of bolts and the design shear capacity of the bolts is more than 6 mm, then we are using a factor. We uh, we will use this factor beta pkg, which is equal to 1 minus 0.0125 tpk, where tpk will be the thickness of the plate we are using. This is our plate, because thickness of plate we are using as a tpk. So as per IS specification, the splice connection should be designed for a force of at least 0.3 times the member design capacity in tension. Design action, whichever is more. Okay, so this is what are the different design requirements for the splices. So the last topic which you might have studied in this week is the introduction to the compression member. So we have already studied about the tension member. So what are the compression members? They are the members, structure members, which are subjected to compressive force along the axis. And what are the various type of compression member we are using in our steel structure buildings is, firstly, the vertical compression member for a steel building is called as stanchion. So if we in RC structure, what we are calling as column, like here, whatever we are calling as column, in case of our steel structure, we will call it as stanchion. And the compressive member in a roof truss or bracing is called as strut. So these triangular section which are connecting our beam to column, and in case of roof trusses, like we will have roof trusses, this type of trusses. So in case of roof trusses, these compressor members are called as strut, and the principal compression member in a crane is called as boom. So you might have seen a crane. So in our crane, the principal compression member is called as boom. Okay. So what are the different modes of failure in case of our compression member? First mode of failure is squashing. So if the length of compression member is relatively small, then the column will be able to attain its full strength or squash load. So squash load is given by yield strength into cross-sectional area. Okay. Second thing is local buckling. So if the individual elements of the compression member, such as web or flange, are buckling, then we are call it as local buckling. If any one element of our compression member is changing, then we will call it as local buckling. Third is overall flexure buckling. So failure due to flexure buckling occurs when there is an excessive deflection of the member in its plane of weaker principal axis. Okay. Next type of failure is torsional buckling. So torsional buckling failure occur due to the torsional moment. The members get twisted about the shear center in the longitudinal axis. And the last type of failure is flexure and torsional buckling. So when these two happen together is when the member bends and twists simultaneously. This is normally because of unsymmetrical cross-sectional area. So what are the different type of compression member we have in our steel structure? Based on their length, we are dividing them as short, long, and intermediate. So in short compression member, the failure stress will be equal to the yield stress and buckling will never occur. And in long compression members, stress will be mainly due to buckling of the member. And in case of our intermediate compression member, failure occur because of effect of both crushing as well as buckling. Okay, this is very simple. And next thing is what are the dividing our classifying our compression member based on the shapes they are we have. So first is angle type. Compression member. So we can have single angle, double angle, or we can have T type. Then we have channel sections, C type, and we can also have some hollow sections which can be in the shape of circle or in shape of rectangular. Then we have these are the type of compression member, normal compression member, rolled steel compression member. If we are having a build-up section or fabricated compression member, then what all we can fabricate? We can have channel section face to face, and they can be connected by other members. And then we can have channel section back to back, which are again connected by other members. And then we can have plated eye section, one eye section which is plated on both hand, and or we can have build-up eye section. What is the build-up eye section is this part and this part, all three are fabricated separately in joint. And lastly, the build-up box section. Same way, we have the four elements which are joined together in the box format. That is why it is called as built-up box section. Okay. Next thing about column section or compression member is elastic buckling theory. So in this theory, this was originated by Euler, researcher Euler. So, what are the different assumption he's taking? First assumption is the material is always homogeneous and isotopic. And second thing is material is perfectly elastic. There is no plastic or any other component in our material. We are assuming it to be purely elastic. Third thing is there are no imperfections. So, our member is perfectly straight and there are no imperfections in our material. And next thing is there is no eccentricity of load. So load is acting axially in the center of our member. There is no eccentricity of load, and the column ends are hinged, and column has no flow. So we are taking an ideal condition. So in ideal condition, we will have our critical stress formula as sigma is equal to pi square A upon lambda square, which is slenderness ratio. So this is the Euler's formula. I hope you all have already studied about this thing. So next thing is strength curve of an ideal strip. So what was strip? In um, the connecting thing was there in between beam and column. That is what we are calling as strip. So usually loaded, initially straight pin ended column. Column fails when the compressive stress is greater than or equal to the value defined by ACT. So this is our graph. This is a graph between slenderness ratio and yield strength Fy. So if uh, our anything is lying below this curve, then it is safe. In case our stresses are exceeding the value of ACB, if it is going in this area, normally we are telling failure is occurring. And next thing is AC is equal to AC is failure by yielding and CB is failure due to buckling. So in this case, we are taking if we assume an intermediate column, so where failure can occur as due to yielding as well as due to buckling. In that case, we will have this type of graph where the straight part will represent yielding and the curved path is representing buckling. So for FC is equal to sigma CR, uh, then in that case, our lambda C will be pi E upon Fy. So if this is a normal metal surface, steel surface, then E will be 2 into 10 raised to the power 5. Fy is 250. Pi we know 3.15. We can calculate lambda C. Right? So that was all about the normal column section, different type of column section, and what are the Euler's formula and strength curve. Next thing is what is exactly affecting the strength of our compressive members. So what are the factors which are affecting our strength? First is material property of the member, what type of material we are using, and next is the length of the member, cross-sectional configuration, support condition, imperfections. So what are imperfections? First thing is we are assuming our material is homogeneous and isotropic if it is not. And second thing is geometrical variation of columns. Third thing is eccentricity of load. And last factor which is affecting strength is the residual stresses in our column section. So we talked about what are the different factors. One of the factors is the length of our column. So how we are calculating our effective length of column? So our effective length of column will be like L effective is given by K into L total length. So this total length we already know. This K factor, it will depend on the what type of end condition you have. If this is our column, what is the end condition at this end and what is the end condition at this end. So depending on our end condition, our K will change. So if both of our ends, they both are pin joined, then our K is given by 1 and IS also say 1. And if both ends are fixed, completely fixed, then K value is given by 0.5. But according to IS 800, it is 0.65. And if the column is fixed at one end and pinned at other end, then it is, then the K factor is given by 0.7. And if the one end is fixed and other end is free to rotate, like in this case, then our K value is given by 2. And next is, if the column is partially restrained at each end, if both ends have partial restrainment, then our K value is given by 1. And if the column's one end is unrestrained and the other end rotate partially restrained, like in this case, then our K value is given by 2. Okay, this much is clear. So now we can go to the different design of column section or compression member. So what are the important parameters we require for the design? First thing is the effective length of column in frames. So this is the effective length formulas for normal column in normal structure. So in case of our frame structure, how we are calculating our effective length? So for non-sway frames, we are calculating K factor as 1 plus 0.145 beta 1 plus beta 2 minus 0.265 beta 1 into beta 2 divided by 2 minus 0.364 beta 1 plus beta 2 minus 0.247 beta 1 into beta 2. Okay, all these formulas are already given in annexure D of IS 800. You can read from there. And second thing, in case of sway frames, how this K value is changing? K is equal to 1 minus 0.2 beta 1 plus beta 2 minus 0.12 beta 1 beta 2 divided by 1 minus 0.8 beta 1 beta 2 plus 0.6 beta 1 into beta 2 whole root square. Okay. So you need not remember all these terms. You can just go through the IS 800 and you will find all this formula directly there. And where beta 1 and beta 2 are usually given in question and beta is given by this equation. So Ka, Kc and Kb are the effective length flexure stiffness of the column or beam meeting at the joint at the end of the column and rigidly connected to the joints. Okay. So next, first thing we have seen the effective length. Next step is the design design strength of our compression member. So in case of a multiple column design curve, we we use a formula based on maximum strength, based on yield limit state, and formula based on tangent modulus theory, and empirical formulas such as Merchant-Rankine formula. So Indian code IS 800 has adopted multiple column curve, which is based on Perry-Robertson theory and is shown in the figure. This is similar to the British code 5950. Okay. So how we are calculating design strength, we have seen different factors. So first thing is, we were saying this Merchant-Rankine formula. So this is the formula which is given to us. 1 upon Fn is equal to 1 upon Fen plus 1 upon Fin. Or we can tweak it in some way that F is equal to Fe into Fy divided by Fen plus Fin raised to our 1 upon n. Okay. And in case of our column section, we are usually taking n value as 1.4. And this is a curve of the allowable compressive strength. So if you see it here, this is a slenderness ratio on this end. So based on the different type of curves, we can calculate our alpha value as 0.21, 0.34, 0.49 and 0.76. Just AB and CD values. And from here we can calculate sigma AC, like point at which we want to calculate our strength value. It will be given by 0.6 into FCC into Fy divided by FCC raised to power n plus Fy raised to power n into 1 upon n. Okay. Then we can go to next thing. Next thing is what are the different buckling class of cross-sectional area. So in case of our I section, what is the limit of I section without buckling is H upon BF should be greater than 1.2 and TF should be less than equal to 40 mm. And buckling usually happen up along ZZ axis and YY axis. And based on this buckling class is given. So similar way, for all the elements, what is the different ratio and along which axis the buckling will be maximized, and what is the different buckling class along that section or along that area. Okay. Next is the welded section. For welded section, again TF is given, TF limit are given. Based on the TF limit, we are telling what should be our buckling class of welded section. And similar way we can have for polar section, welded box section, channel section, T section, solid section, and many filled up members. Okay. So next thing is how to do the design strength of our compression member. So as we are studying since the first week that our strength should always be less than or equal to the design strength of our system. So same way we are using P should be less than PD, where PD is given by the overall area into eccentricity AE into FCT. Okay, where A is the effective cross-sectional area and FCT is the design compressive strength. So FCT is given by a formula, this formula Fi upon gamma m naught into 5 plus, divided by 5 plus pi square minus lambda square raised to power 0.4. And it should be always less than Fi upon gamma m naught. Okay. So these are the different stress reduction factor. Here we are seeing many terms like uh, gamma, phi, gamma. So this can be calculated from IS 800. So this is Xi, stress reduction factor. From stress reduction factor, we can calculate the KL upon R value. So if our stress reduction factor is say 0.342 and our Fi is 250. So this will give us 140 number. 140 of slenderness ratio. So based on our Xi and Fy value, we can calculate our slenderness ratio. Similar way, in from our value of FCD and FY, we can calculate our slenderness ratio or vice versa. Okay. So we are calculating our slenderness ratio, but to check for our slenderness, we are applying some allowable slenderness ratio check. So this is also given in table 3 of IS 800. If we are having loads, we are having dead load and superimposed load, then our slenderness ratio is by 180. If it is wind and seismic, 250. If there is no roof truss or bracing member, then it is 350. And next is the, if we are only using lacing bars and column, then it is 145. And if we are using any other type of element in a built-up section, then it is given as 50. Okay, so this is all what you might have studied in week 6. Next, we can see some problems which will help you solve the assignments of this week. Then we're going to the first problem. Actual length of the column is 3.5 meter. What is the effective length of the column with one end unrestrained and the other end rotation partially restrained? So we discuss about effective length, that L effective is equal to K into L total length. So the total length is given by 3.5 meter. And what is the effective length? And the other end partially restrained. So for this case, what should be the K value? So if we see here, we are telling one end is unrestrained and other rotationally partial. So if our one end is restrained and other partially restrained, then we are telling, our L effective is given by 2 times of L. Here our effective length is 2. So the answer is 7 meter. Okay. Okay. Then the next question is, what is the allowable slenderness ratio of lacing bar in a column? 50, 145, 180, 250. It's a very simple question, subjective. So for the case of lacing bar, we are telling our slenderness ratio is given by 145 megapascal. Okay. So we'll go to the next question then. So that's the answer also. Okay. Question is, if a lug angle is connected to the channel section, then lug angle and their connection to gusset plate or other supporting members shall be capable of developing strength not less than 5%, 10%, 15%, 20%. Answer is already given. It's 10%. We have also seen that we are having 2 cases in case of angle section, how the strength is changing, and in case of lug angle, how strength is changing. So the answer will be, it should not be less than 10% in excess of the force in flange section. Okay, then we'll go to the next question. The vertical compressive member in steel building is called as, we have already seen that if we are using normal vertical compressive member in a steel section, it is called as strut. Sorry. So this will be called as strut. Okay. Next is, among the following option given, which is not a mode of failure of column. So we have seen 5 type of failure mode of column. So which of them is not? Shear failure, torsional buckling, squashing, overall flexure buckling. We read about, we started our mode of failure from squashing. flexure will be there, torsioner will be there, and then flexure and torsioner will be together. Then who is not there? Shear failure. Okay. So the answer is shear failure. So the next question is a numerical type question. Is So this is our next question. A column having actual length equal to 3 meters is fixed at one end and pinned at other end. Calculate the critical load that column can take using Euler's formula. Here take Young modulus as 2 into 10 raised to 5 MPa and moment of inertia as 52.6 into 10 raised to 4 mm4. So actual length is given to us and condition is given to us. We can calculate the effective length. So what is given to us? One end is pinned and other end is fixed. So in that case, we are taking K as 0.8. So the effective length of our column is given as 24 mm. Next thing is we have to find the critical load. P is equal to pi square EI into upon L effective whole square. So we have pi square. E value is given to us as 2 into 10 raised to 5 megapascal. Moment of inertia already given 52.6 10 raised to 4 mm4. And L effective we have already calculated. So from here we can get the critical load, which is coming as 180 kilonewton, 180.26. So it is between 180 and 181. So accepted answer is B. Right? Okay. Then we'll go to the next question. Calculate radius of gyration of an ISLB 300 at 37.7 kg per meter about x-axis, whose I-axis is given by this value, I-y-y by this value, and area as 4808 mm². So how you will calculate this thing? So radius of gyration is given by under root of I upon A. So about what we will calculate it about x-axis they are asking. So about x-axis we only need I-axis. So using that formula we can get radius of gyration as 123.5 mm². Okay, simple question. So next question is, eighth question is, the design shear capacity of bolts carrying shear through a packaging or filler plate of thickness TPK in excess of 6 mm shall be decreased by a factor B beta pkg is equal to, this formula we have already seen in previous slide. So what is the correct answer? Beta is equal to 1 minus 0.0125. 1 minus 0.0125 into TPK. Okay. Fine. So the next question is, calculate the minimum number of bolts required to connect the outstanding leg of the lug angle to the outstanding leg of the main angle if the load on outstanding leg of main member is 120 kilonewton and the bolt value is 36. So what is given to us is load on outstanding leg of main angle 120 kilonewton. Then bolt value is 36 kilonewton. So how we will calculate number of bolts? It is given by 1.4 into load of leg of main angle divided by bolt value. So from here you will get the number of bolts required and it is coming as 5. Okay. So the 10th question is, what will be the value of critical slenderness ratio lambda c of an axially loaded initially straight pinned ended steel column having yield stresses 250 gigapascal. So slenderness ratio can be calculated using this formula. Lambda is equal to pi into under root E upon Fy. So pi we know constant. Fy is given as 250 and E will be always from iron or non-metallic into 10 to the 5. So using this formula, we can get a critical slenderness ratio and it is coming as 88.85. So the 11th question is, which of the following features Euler's ideal column should have? That firstly, material should be perfectly elastic, column and are hinged, column have no flaw, and material is homogeneous and isotropic. So according to this, what all Euler's proposed. So this is what Euler is proposing. If material should be homogeneous, isotropic, perfectly elastic, no imperfection, no eccentricity, column and should be hinged and there should not be any flow. So answer is all the four options are correct, right? So all the four options are correct. First question is the imperfection factor alpha for buckling class D is given by. So the imperfection factor alpha of buckling class D is, if we see the imperfection factor table, table 7 for IS 800, for buckling class D, it is given as 0.76. Okay. Okay, so the last question is calculate the number of M18 grade 4.6 volts required for the connection of member OC as shown in figure below. Thickness of the gusset plate is equal to 14 mm. Assume pitch and edge distance as 50 and 35 mm. Consider Fe410 grade of steel and assume that given loads are multiplied with suitable factor of safety. Okay. So what is given to us? Main member is of which ISA 100 into 65 into 8, having a load of 520 kN in one end, 268 other end. Then we have two plates joined using gusset plate, where one is IS 90 by 60 by 8 and other is 90 by 60 by 6, and the loading is 150 and 170 kN. So what is we are assuming the diameter, sorry, it is given diameter of bolt is 18 mm. So taking extra clearance of 2 mm, we are getting diameter of bolt hole, which is given as, which will be calculated as 20 mm. So next thing is calculating net tensile area of the bolt A and B. It is given as 0.78 pi by 4 d square, and D will be taken as 18 mm. Using this, we are getting net area of bolt as 198.48 mm square. Next is shear strength of M18 bolt in single shear. So shear strength formula is given by this FUB divided by under root 3 NNANB plus NSASB. So FUB is 400, and then number of bolts in number of bolts in S direction, in shear direction is 0. All the bolts are in tensile area, so we are telling only one bolt is there. So 1 into area, we have calculated 198.48. So here we can get the shear strength value is 36.67 kilonewton. So in case of double shear, if we are having double shear as given here, in case of double shear, we will multiply the shear strength by 2 and it will give us 73.34 kilonewton shear strength. So what is given to us? Pitch is given as 50 mm and distance as 35 mm. So KB will be least of E upon 3D naught, P upon 3D naught minus 2.25 and FUB upon FU and 1. So all this formula we have already studied in tension member. Oh, sorry, before tension member itself. So KB will be given as using all this formula. We have to use minimum of for all these four things. So KB is given as 0.583. So now how we are calculating in this member, in member OC, our force is given as 170 kilonewton. So and the bearing strength of bolts on 8 mm thick angle will be given as 2.5 into KB into D into T into FU upon gamma MB. So all using all the equation, KB we have calculated 0.583, diameter calculated 18 mm, and then thickness of the plate also we have to consider here 8 mm. Okay. Thickness is given as 8 mm. Yeah, for this member it is 8 mm, and then FU upon gamma MB. FU is 410 and gamma MB is 1.25. So using this formula, we are getting BS strength as 68.84 kilonewton for this angle section. Next thing is the strength of angle per pitch length. So strength of angle per pitch length is given by 0.9 FU into AN divided by gamma M1. So FU is given as 410. AN net area will be given by total end distance minus 20. 20 will be was our bolt hole into thickness of plate, and then divided by gamma m1 as 1.25. We are getting strength of angle per pitch as 70.84 kilonewton. So the bolt value is 36.67 kilonewton. How it is calculating? We are calculating three strengths: TDN. We have calculated three strengths: TDN, then bearing strength 68.4, and before that we have calculating the shear strength of bolts in double shear 73.34. So minimum of all three strength will be taken as our bolt value, which is equal to 36.67 kilonewton. So the number of bolts required, how we can calculate number of bolts required is, this force is 170, 170 divided by strength of our bolts, which is 36.67. So the number of bolts required in this plate will be 5. Okay, clear? Okay, so that's all for this week. If you guys have any doubt, you can ask me, or you can mail me also, mail ID. Thank you, everyone.